Okay, so welcome also from my side. I'm a faculty in the Institute for Data Systems and Society and in the Department of Electrical Engineering and Computer Science. And it is with great pleasure that today I'm going to introduce the plenary speaker of this morning, Esther Duflo. Esther is the Abdul, Latif, Jameel Professor of Poverty Alleviation and Development Economics in the Department of Economics here at MIT. She has received numerous academic honors and awards for her research. Just to name a few, she's a member of the Academy of Sciences. She's a corresponding fellow of the British Academy. She won a MacArthur Genius Award. She won a John Bates Clark Medal, etc., etc. So in her research, she seeks to understand the economic lives of the poor with the aim to help design and evaluate social policies. And we'll hear much more about this during her talk today. Esther, I'm very happy to welcome you here to give your talk and very much looking forward to it. Thank you.
Thank you very much. It's a huge pleasure to be here. So I feel somewhat like an interloper because I'm not a statistician, although I do run randomized control trials. But one nice thing about randomized control trials, the statistic is pretty easy. Generally, we need to compare treatment and control, and it can be described in bar charts, and it gives you a pretty good handle on causality. But inspired by whatever is happening in the Institute, by my colleague Victor Tchernozukov, who I think is a pillar of IDSS, and Alberto Abadi, I kind of got interested in seeing, well, can I kind of educate myself in other pieces that would be relevant? And therefore, I have started working on various topics that people here are interested in. One of them is social networks. I know a lot of people are interested in social networks. And the other, to some extent, is machine learning. I think I need to be away from the microphone. To some extent is machine learning, and in particular, how you can combine randomized control trial and machine learning methods, and in particular, how machine learning can help us interpret the experimental results in a richer way. So when I was preparing for this talk, I thought, okay, what could I do that kind of illustrates all of these things coming together for one societal issue. And in fact, it was very easy to think about because one of the projects that for which the data collection recently finished and that we are working on is a project where all of this comes together in the context of immunization. So immunization is pretty essential, probably one of the best buy in public health worthwhile. It prevents illness, disability, death from diseases that can be prevented by vaccines, including hepatitis, measles, that we are talking a lot these days, but of course have always still been present in developing countries. Global coverage of immunization is not bad. It's 85%, but it's not great because it really should be 100%. And it's not really improving in the sense that the last 15% seems to be a little bit difficult to reach. And in particular, the WHO estimates that if kids received the standard package of immunization, don't even think about the newer ones, we could avoid 1.5 million deaths if the global immunization coverage improved. In practice, about 20 million children every day don't get the penultimate vaccine in the sequence, which is DTP3. And a lot of those children live in very few countries. Some of them, of course, have complicated situation, like Afghanistan or the DRC. But others, like India, for example, is actually a middle-income country by now, one which has a functional society in general, and in particular a functional public health system that has done a lot of effort in trying to make immunization available to people, usually very close to their houses, through mobile clinics, etc., and where, in particular, in the whole north of India, immunization rates remain very, very low. In particular, in the area we work with, which is the state of Haryana in India, where the capital of India sits. So it's not exactly the most remote place in the world. has full immunization rates that are north of 60%. So that means 40% of kids don't get measles, for example, which is the vaccines that, of course, we are all talking about these days. So until now, and that's true in India, that's true also in a lot of other developing countries, the focus has really been on supply, with the idea that if the immunization services were available, and they were available close to people's homes, then they would just go and get immunized. But despite all of this improvement in supplies, first of all, the improvement in supplies are very difficult to effectuate, because once you want every single nurse to go to every single villages, monitoring that has proven very difficult. And then even when that happens, I've done a small experiment a few years ago showing that even if you manage perfect, absolutely ideal implementation of immunization camps in villages, you still have many people who are not going. So the lack of demand for immunization is likely a key reason for low immunization rates in India, and you could, in some sense, improve supply until you are blue in the face without being able to really make significant progress. So how does one change the demand? So one possibility is to try and change people's core beliefs. And that's, of course, very difficult. That's not really my area of trade necessarily. But in general, in public health literature, information campaigns trying to change persuasion, etc., turns out to be very, very difficult. If people have a strong view that they think immunization causes autism, for example, or is designed to sterilize them, or whatever it is hard to make them change their mind. On the other hand, it turns out, and from previous research, we have very clear evidence of that many people actually are perfectly fine immunizing their kids. In fact, most people start the immunization sequence. About 95 to 98% of kids get the BCG in India, which is one you get at birth. You don't get in this country, but you get in Europe and India. So people are not against, and when you ask them, they think immunizations are great, and they think it has lots of benefits and very little cost, and they all plan to do it, but they kind of don't get around to do it. So it's not to say that there is not a small minority of people who are dead set against immunization, but for a country like India, it's a minority of the people who actually don't end up immunizing their children. So a lot of my research over the last few years has been about leaving these people aside. How do you reach the people who, in principle, are all in favor of immunizing their kids, except that somehow don't get around to do it? So I'm not interested in shoving people, but I'm interested in nudging them. So how one can do that? Well, one of the reasons why people do not get around to immunizing their kids is because they think they are going to do it next month. So basically, we all have, and you can just introspect for a minute, you will see that we all suffer from a tendency to procrastinate. So if I think there is a small cost to getting the kids immunized, I have to take a half day off. The kids might be starting not going to like the needles, and they're going to cry, and then they're going to maybe develop a small fever and all of that. Those small costs are better incurred in a month than today. In turn, the benefits are at some unspecified point in the future where instead of getting sick with measles, you don't get sick with measles, but it's sometime later. There's no urgency. So for any problem like that where there is no urgency and there is a small cost today, these are the type of things that you will tend not to do until there is a deadline, but there is really no deadline in terms of immunization. So you could constantly kind of postpone it till the next month. So if that's the world in which we live, one possibility is to impose a schedule. That's what's been done in this country, where the pediatrician tells you have to get the shots by such and such time, and otherwise getting to school is a hassle, etc. In a country like India, it's really not practical, because you can't enforce a schedule if you're not even able to really make sure that the services are there in a reliable way, and you can't monitor that it's being done anyways. So several things you can do. One is to kind of offset the small cost of the immunization today with a small benefit. So we ran an experiment many years ago, 10 years ago in Rajasthan, small experiment, concept experiment, where we gave people in randomly selected villages, first of all, we fixed the supply problem. That's what I was talking about before, by making it perfect. Very regular immunization services. And second, we added small incentives for immunization in the form of the bag of lentils. And that had very large effect on immunization. The full immunization rate went from about 5% in the supply-only group. Sorry, 5% when we did nothing, 12% in supply only, 37% when we added the incentive. So that was something that's been on the back of my mind to try to do this on a much larger scale. The second thing you can do is to remind people, so kind of increase the salience, brings people top of mind, immunization top of mind. So that you can achieve, for example, by sending people reminders. So this is something that people also talk about in the context of reminding people to take their medication. For example, diabetes medication, blood pressure medication, you can ping people. Partly, it's not that people don't want to do it, but there are too many things to keep in track of. So the reminders can help. And the third thing you could do, in particular, if you were a little bit worried that the reminder would get lost in the shuffle, is to use human contact to do that, and in particular, to leverage the social network. So the idea there is to identify people who are influential in the community, who know a lot of people, who know a lot of people, who know a lot of people, and can spread the message that immunization a camp is coming and immunization is important. And potentially, of course, all of these things kind of can reinforce each other. In particular, if you have an incentive program but nobody is aware of it, that's not so useful. So if you have an incentive program and you have a central person that you can inform there is an incentive program, they can spread the message. So ever since that very first experiment that we did in Rajasthan a few years ago, I was trying to replicate that on a much larger scale with the government, and eventually succeeded to work with the government of Haryana in 7 districts that had particularly low immunization rates. A district is a bit larger than a county. It's like quite a few people. And we did a few things there. So the first thing is to set up a tablet system, like an e-health system, which was actually set up by designed by a group here called Sana Health, by an MIT group called Sana Health, to collect data and have an information system for immunization for the entire place. So that itself covered, you'll see the number of kids in a minute, but about 2,400 villages in those places. So that basically this is a tablet that nurses carry to the immunization sites, and in which they enter all the shots they're giving on a given day. The children are tracked with a unique ID system unique to our software, so we can know their history, etc. Using that, leveraging that platform, you can do a number of things. So first of all, you have data. I'll show you in a minute that you need to make sure it's good data, and we spend some amount of effort doing that. And then you can also, since you have what they are due for, you can send them reminder. It's essentially free. And once people have received a shot, you can give them an incentive in the form of a cell phone recharge. So we did that. So we set that up. It was longer than it is to describe it, because that software is actually, the data architecture is actually much more complicated than I thought it would be. But it was done. And then on top of this thing, so we kind of set up the experiment. I'll show you the design in a minute. And on top of this, in about 900 of those villages were organized to do the social network experiment. So what we are doing, what I'm going to talk to you about today is give you some of the results, basic results of what we get when we do all these things. Describe the social network experiment in detail, because there is some cleverness to it. And finally, I'll talk to you about the machine learning exercise that help us determine where the intervention is most effective, which is very, very relevant because we actually are in conversation with the government to scale this up. And they're willing to scale up the social network experiment to everywhere because that's not very expensive. But for incentives, for example, they want to do it where it's going to be the most effective. So we need to guide them towards that. So just to give you an idea of what's a randomized control trial, I guess you know, but just a visual idea, this is one of our districts, Sonipat. There are many, many villages in Sonipat, but the villages are organized around primary healthcare centers that cover about 10,000 people each. The primary healthcare centers are sort of an administrative unit with several nurses on it who talk regularly with each other. So the incentive experiment was randomized at that level. So for example, in this district, you have incentive primary healthcare center and control primary healthcare center. So that's an example, sort of visual example for one of the districts. You multiply by 7. That gives you the number of PHCs that are covered. And I told you the number of villages, about 2,400. So I had gone through the various treatment we had in experiments. So as you can see, it sort of gets a little bit intricate because we are trying to do many things at the same time. And we still need power to be able to distinguish hypotheses. So we believe that the incentive experiment could only be randomized at that larger level of the primary health center level because nurses talk to each other and you can't really have incentive somewhere and not elsewhere because they're going to be totally confused and upset. So we started by dividing the PHC into 70 treatment, 70 control. Then one of the things that is interesting is how much do you need to pay? Like what's the level of the incentive? And whether you gain by, because there is dropout in immunization, do you offset it by having a slope where the incentive for the DPT1 is very low and the incentive for measles is very high or higher. So we separated the incentive within each of the PHCs. The schedule of incentive was different. So each PHC then has several subcenters. And so within each PHC, we divided the subcenter into different forms of incentive. High flat, high slope, low flat, low slope. So with basically level and slope different. Then the reminder, the targeted reminder can be randomized at the individual level. It's trivial to do. We were interested in whether there are spillovers. So we first randomized subcenter in being no reminder at all versus 33% of people receive reminder versus 66% of people receive reminders. And then people are randomly selected, individuals are randomly selected once they first show up to receive the reminder or not. And the reminders are basically telling them you're due for the next shot. So that's for the incentive and reminder experiment. Then in about 1,000 of those, we run the social network experiment, which was randomized at the village level. I'll describe the nature of that experiment a little bit later. But that's overlaid on top of the incentive experiment. So in that 1,000 village sample, we kind of have everything floating around at the same time in a fully stratified cross-randomized way. Just to give you a sense that it's much quicker to give a talk than to actually do these things, when we first approached with the government and first started to design this was actually way not in that chart in 2014. And then we talked to them, finally designed, et cetera. Finally, we got approval for the study in 2016. We did a baseline, the SANA group developed the application, tested it, and the program was launched in March 2017. Then it lasted for about a year, and in July 2018, we had the data finished. So the first thing that was kind of had to be done was this data information system that we had to put in place. Many countries are now progressively introducing a mobile health platform, but there wasn't one at the time. So we kind of designed it, a very bearable one, simple one to collect immunization. So what the nurses do is that after they've immunized the kids, They write down in the tablet the child information, the unique ID system that every Indian has. In Haryana, it's very frequent. What vaccination they give and the phone number. Then it goes to a server that we were maintaining. And then that allows to provide a monthly report for the administration and mobile recharge and SMS, and is also the source of the data I'm going to show you today. So just to give you an idea of how many people were in the system, so about 300,000 kids were in the system at some point or another, and of those, most of them got more than one shot. 74,000 of them were fully immunized by the end of the program. It's not to say that these kids would not have been immunized without us, but at least we are capturing their immunization level now. So that was the kind of the official data collection. In addition, we did a few things. We were regularly checking that the system was being used and apparently used well. And then we really wanted to know whether the data was going to be usable for us. What was the quality of that large amount of data that was being generated? So we did these child verification surveys where we randomly selected kids from the tablet data. We went and visited them at home, and we asked them what immunization they had received, et cetera, to then cross-check again the administrative record. And then we also did kind of a more qualitative surveys in 200 villages to get data on people who never showed up to the camps. First things we had to do is to train the A&M. So if you want to train 1,400 A&M who's never seen a tablet to use the system, that's kind of a project. So it happened in a sort of cascade kind of a way, where we trained the trainer, we trained the A&Ms. It went remarkably well. They actually were excited, which is good, because my previous experience working with nurses in India had been somewhat conflictual, that they don't really like people meddle with what they are doing. But they saw the tablets were fun, and in fact, did a very good job with it. So what we did then is to regularly, use this to gain the A&M interest. The application was simple, and we kind of empowered them with them. To gain the administration interest, we use it to provide a report for them regularly. And the A&M did a good job. So for example, they didn't fake records, which was something we were kind of worried about. So mostly we can find all of the kids in the tablet, they exist, which is a good thing. And most of the information is correct. The child name is correct, the date of birth is correct. Sometimes the vaccine entered in the tablet, it says only 76% correct, but you have to think that parents are not necessarily very clear of what they got. So it's not, when it says correct, it means it matches. But I would tend to believe the administrative data once actually the child is the right child, and people actually remember that they've come. That the nurse is much more likely to know that it was DTP3 than the parents. So that means that this means several things. The fact that the data is OK means several things. The first thing is that our incentive program is not compromised. There was no widespread cheating or something like that where all of the incentive went to the friends of the nurses. It also means that we can use, and we will use, the administrative data as the main outcome. So that gives us, instead of having to rely on survey, we have the whole data to play with. By and large, so again, this was a pretty big enterprise to get all of this data together, to get the application to work, to maintain the server, to transfer the information from the server to the provider that was giving the recharge, etc. So by and large, it worked out. We got about 90% of the recharge, 90 to 99% of the recharge were delivered successfully in a given month. The text message were about 80% of the text message actually reached their beneficiaries. We don't know if they were read, but we know they were received and open. So that's good. So it seems that we have actually, after all of this kind of work, we actually have an intervention that we can study. So what do we find? So let me go back to describing each intervention in a little more detail and then the result for it. So for the incentives, if you remember, we had 4 types of incentive. We had flat payments, either at the low level of 50 rupees per shot. That corresponds to 70 cents, something like that. Or at a high level of 90 rupees per shot. And then we had a low incentive increasing payment, so 10, 10, 60, 160, 250. So the overall cost is the same, but it's sloping up, with more for measles, where the drop-off is the biggest, and a high incentive with a slope, where now the payment for measles is 200 rupees. What do we find? So to read this table, in the bottom line, you have the control means. So how many? This is data that is presented at the subcenter level, number of things per month in logs or in levels. So for example, the last column is in a given month, we saw about 45%, 44.9% kids showed up in any subcenter. And you can see that, so that this is in the control group when nothing was done, when there was no immunization. And with the slopey incentive, it went up to 50. And that's quite significant. The stars are telling you that it's significant at the 1% level. So basically, we got more kids, and we got more, about 13% more kids immunized in the slopey incentive. And we got 0 effect of the flat incentive. If you further divide the slope by high slope versus low slope, they turned out to be equally effective. That means, of course, that low slope is much more cost effective. But what seems really to matter, rather than the level of the incentive, is that there is a progression, which kind of offsets the tendency to drop out. So that's the effect of the incentive. So an improvement of about 12% in the number of kids who got fully immunized, or 13% in the number of vaccines that were given on average. So we were happy. These are lower effects than the one we had in Rajasthan, but it's a much larger scale, much less salient, because it's just this recharges. It's not like you go home with your kilo of lentils. But of course, it can be, it's very, very straightforward to administer. So that was kind of a first nice result. Then how about the reminders? So the reminders, there is a literature in psychology and economics suggesting that it's kind of this like golden experiment, because it's essentially free and you can just do it, and you bring issues top of mind and people will do it. Now, the problem, there are a number of problems with that. The first one is that a lot of people think that, and so we get a lot of reminders. So in the end, there are a lot of issues competing for our scant attention through these reminders, and that might dilute the effect of it. Another issue that my 2 of the co-authors in this project, Abhijit Banerjee, in fact 3 actually, Abhijit Banerjee and Arun Chandrasekhar has found, is that when you try to convey an information that could be a little bit complicated, a tiny bit complicated, for example, immunization is not super complicated, but it's still you have to think about whether it's something that's good for you, you have to think about it. Broadcasting it to everyone might make people shy about going to other friends to ask them for clarification and whether they really understood what this is all about, because if you know that they know that you have the information, like you look like an idiot if you have to ask for extra advice. So in the context of demonetization in India, which was this interesting moment where all of the bills were removed from the Indian economy for a while, and then when they were reintroduced, there were many, many, many difficult, complicated rules. And they tried to broadcast through actually even to talking to people information about these rules. And they found that it was counterproductive in the sense that people didn't quite understand what was being told to them, and they didn't want to ask anybody's advice. So broadcasting this information to people might be less effective than finding the right people explain it to, which then people can come to understand what they are talking about. So this is just to say that in principle, it could have gone both ways, even though people tend to think of reminder as this complete sure win that one should do anyways. So in this case, what we find is like nothing. So it was not bad, it was not good, it just did nothing. So what you have in this regression is the first column, so the control mean is the same as before. It's the number of, this is the number of shots by month. And you have, or log shots by month. I don't know why we don't have total number of children that was 5 before. So you can look at measles, for example. In an average month, in an average subcenter, 2 kids come to get their measles vaccines. If they are in a reminder villages, which means anybody got a reminder, not necessarily them, that doesn't really increase. And if they got the reminder themselves, that also doesn't really increase. So it looks like the reminder didn't do very much on average. So given that the reminder didn't do very much on average, did we get more leverage by talking to the influential people in the community? So in order to decide whether to immunize your kids, you must have some knowledge of the cost and benefit of immunization. Where is the camp? When they're going to come? Because they don't come every day. They come to a village roughly every month. But you might be able to go to neighboring villages if you're free on a given day. Of course, if there are incentives, people need to be aware of them if they have to have any effect. And they were not advertised very heavily. They had some posters, and that sort of was relatively limited effort there. So to communicate this type of information, increasingly governments want to rely on informal social networks. So not only information on health, but information on new agricultural technology. And of course, this is something that farms do. For example, some of you might remember of the launch of Gmail. Gmail was not advertised. A few people got access to it, and then they got some invitation. So even when there is the possibility to broadcast, because of course Google could have broadcasted Gmail, they chose to go through informers, probably for reasons similar to what I was describing before. So then the question is, who should you give the information to if you're going to have, want to look for a particular, what we call seed. If you want to seed your information, who is the right seed? So what you want is someone who is going to, if they have the information, have a position in the network, which means that when they give it, they have many friends to give it to. But more importantly, their friends themselves have many friends. So in the social network jargon, what this means is to be central. So I mean, illustrate the idea of centrality with a measure that we came up with Matt Jackson and Arun and Abhijit Banerjee, which is what we call diffusion centrality, where we want to imagine a process which lasts for a few periods. Because frankly, diffusion processes are not usually infinite because people get fed up of talking about immunization. So let's say you talk about it for 4 periods. You have 4 conversations with people on this process. And suppose I diffuse and then maybe not with 100% probability. Maybe you don't talk to all your friends. So let's imagine, just for the sake of this graph, a diffusion process which lasts 4 periods, and where you talk to any of the people you're connected to with a probability 0.5. So here the person is, my initial node is green, and what we have here is the various people in the network, and the link represent the links represent that they are friends. So my green person got the information, then they diffuse it to one of their friends, and then it starts again. So this one friend diffuses to some more of their friends, and the green person diffuses it again, and it continues like that. And after 4 periods, on average, this person I've graphed it such that it's also the average. This can be computed. So this person diffusion centrality is 13. And if you knew the shape of this network, the entire social network matrix, you can compute the diffusion centrality for any length of the period and for any p, the probability of passing. So he's a person who is less central. So we can see that after 4 periods, they only managed to reach 6 of their friends. So the idea is that you want to diffuse information. You want to find people who are central, who have high diffusion centrality, or another way to think about it, if the process gets long enough, is high eigenvector centrality. The eigenvector centrality is the equivalent of your Google rank page. You know many people who themselves know many people. So that's all well known. It's been shown both non-experimentally and experimentally that indeed when you diffuse information to these central people, the information circulates faster than when you diffuse information to any random person. The problem is that if you're the governor of Haryana, you have 7,000 villages, you're not going to go and collect that network map. It's not happening. If you were going to do that, you could just talk to every single person, right? So the question that one can ask then is, how can I collect information on who is central without going through all the trouble of collecting the entire network map and doing the matrix algebra? So one sort of natural idea, you might think, is to ask network participants. So just go and ask a few people, hey, who is the mover and shaker in your community? Who is, when they come to know about something, everybody comes to know. So if you introspect once again, you can see that maybe in your department or in your group of friends, you know who is the central person. Surprisingly, it is not a strategy that people really had ever used. And one reason is that, although by introspection we seem to know who are the people who are diffusion central in our networks, when you think about it, it's like, why would we know? Because it turns out that people, even in this small community, have a very, very poor image of the social network in which they live. So if you ask them, who are your friends, they, of course, know who their friends are. But if you ask them who the friends of their friends are, they have no idea. And of course, the friend of the friend of their friend is not like, is no view. So people don't have the whole social network mapping in their head, so they cannot calculate diffusion centrality. They can't do it. They don't have the information. So a priori, it would think that that's not something that people should be able to do. So in previous work, we have a very simple theoretical result. And we show that, in fact, it works in practice, in kind of test case experience, which shows that even though people might have a very poor idea of their network in general, they still could know who are the influential people. And the magic of it is that it works in reverse, which is someone who is very good at collecting information is also someone that you will tend to hear about. So imagine, for example, that people are sometimes hit with news like, my brother got a child. My brother did get a child on April 1st day. And then so now like some 200 of my closest friends just learned this fact that Esther's brother got a child, and then you're going to diffuse it to your friend, and you're going to diffuse it to your friend. And after some time, you might know how many times you've heard that news that Esther's brother got a child. And if you've heard it many times, it means that there is many route that goes from Esther to you, and therefore that must be someone who is fairly central. And if the process of information are long enough, so even with a very short diffusion process, it's correlated with centrality. And if they are long enough, it actually is eigenvector centrality. So that's, so the people that we hear about a lot, even if we don't know them ourselves, must be people who are quite central. And therefore, I could go to you, or to a few of you, and ask who are the influential people in your network, and you should be able to tell me. And what we did in our test experiments, which was in Karnataka, another state in India, is we went and asked a few people in the village, and the first result is that they all point to the same people, which is, of course, what you would expect if they are good at identifying them. And secondly, when we give information to these people, it indeed circulates very fast. So there, we just applied the same idea on this much larger scale. We went to the villages, interviewed at random 10 people in each village, and say who is influential. So the way we asked is this kind of this script, which is a little bit cumbersome, but get the idea. who are the people in this village who, when they share information, many people in the village get to know about it. For example, if they share information about a music festival, street play, fair, movie shooting, many people would learn about it. So we were very careful to not give a message that was specifically about immunization, because we want to know who is good at diffusing information in general. And then this is because they have a wide network of friends in the village, and they could use that to actively spread information to many villagers. Could you name a few of those? So that was our gossip experiment. We call these gossips. We call these guys gossips. The government wants to scale this up, but they want to call them change agents, which seems fair enough. So we call them gossips, and then we are going to contrast. So we identify those people. We went to see them, and we enrolled them in the program, saying, all you have to do, we are going to send you an email once a month to remind you of the immunization camp and incentive villages to remind you that there also is an incentive. Just transmit it to your friends as you get a chance. We contrast that to random seeds, so randomly selected people, same thing. People that we elicited to be trusted, so where we ask people who is generally trusted in this village, which is a much harder question that we don't have a result that people should know that. And who is a trusted gossip. So both good at conveying information, and in addition, people tend to trust their advice. Then we contact them, and we let the process go. And what we find here, so again, this is in comparison to about, let's say, for number of children, about 5 children get immunized in every, no, sorry, because this is now at the village level, so I don't remember what the mean is. So we can look at the logs, and that will clarify the thing. But in villages where we hit a gossip, where we hit the gossips, we immunize about 8 more kids in every month than in other villages. And you can see that when you hit the random gossip, it does nothing. If anything, the point estimate's negative, but it's very small. And the trusted and trusted gossips are, if anything, less effective. Although, to be fair, you cannot distinguish that these are statistically different. But what seems to be dominating is this idea is the gossips. And it works for any number of immunizations. So on average, in places where we hit gossip, we immunized 24% more children than in places where we did nothing. So that's great, because this gossip intervention is really, really cheap. Very, very easy to do. And so this is something that they could replicate. So remember that in those villages, we have everything done at the same time. So in the table that I had before, I control for the other intervention, but we can also compare them. So this is for the number of kids who get measles in a given month. And you can see that the gossip seed have the gossip treatment. So each of these is a treatment effect compared to doing nothing, compared to the pure control group. And you can see that the gossip treatment is the largest, actually. And it's even larger than the high slope incentive. In these villages, the high slope actually happens to be bigger than the low slope. It's even larger than the high slope, which is much more expensive to do. So the gossip seems to be something interesting to do. Then another thing we did, and I'm going to show you this slide, but it's keep in mind that I don't go home necessarily thinking about this as the last word on this, is actually now you can think of in these 1,000 villages. Here I have aggregated the policy, so any place that there is gossip, there is a 1, and I'm comparing to nothing. But in fact, we have gossip plus incentive plus reminder, and so we can look like which is the one that works the best. So this is what we find, and unfortunately, the one that works the best is the lightest. But interestingly, the policy that works the best is gossip plus incentive plus reminder. So it's doing the whole package. And for us, it makes perfect sense that the gossip intervention is more effective in combination with the incentive. This is what we had predicted and what we wrote up in our pre-analysis plan. Because in the absence of incentive, the gossip don't have any pieces of useful information to convey. It's just like propaganda. So people might or might not pay any attention to what's being said. And in fact, if anything, we find that if you give gossip in non-incentive villages, the effect is negative. So this guy is keeping to repeat you that immunization is important. It's kind of annoying, and it's like there must be something weird there. On the other hand, when you have incentive, there is actually a piece of factual information that comes up, which is, hey, if you get your kids immunized, you're getting a recharge. And so it makes perfect sense that, I don't know how to go back. So, oh, yes. It makes perfect sense that the effect is the largest when you're combining the two. The reason why I don't want you to go home with thinking that is necessarily the truth, I'm super confident in the previous slides, but this one has many policies. And when you have many policies that you're trying to compare, it's a little bit the same issue as in any machine learning exercise where we start to have the possibility of overfitting. So here it's kind of interesting that it lines up with priors. That's encouraging. But I think we need to do a bit more work to think about how to get the right p-value for this thing. And I'm not sure the p-values are exactly correct. But this is where we are. So next question then, since we now have the ear of the government, they are interested, they are developing, they are rolling out their own e-health technology so they can continue with that. So first, what kind of advice we want to give them? Well, we want to give them that you can do gossips, and in particular, you could maybe combine gossip and immunization. Gossip and incentive. But then if they are going to combine gossip and incentive, they won't do incentive everywhere because that becomes expensive. So the next natural question they ask us is, then where should I do it? If I have limited resources to do incentive, where should I do it? So for that, we need to understand whether the effects are heterogeneous from place to place, and what are some of the available variables you can use to help them guide where they should send their resources. And of course, it's a big issue in randomized control trial that many people are trying to do. Every time you have a randomized control trial, usually you have some subgroup. The problem is if you start looking for subgroups, ex post, who knows, it could just be luck or whatever, and if you look for enough subgroups, you're going to find some that are going to turn out to have different effects than others. So in medicine, you are not allowed to give subgroup analysis unless they were pre-specified and you stratified by them. Because people are the FDA is very, very concerned about, yes, my drug doesn't work, but for people who have red hair and green teeth, it's really fantastic. Because that might not actually be real. So one route is to do what we did, which is to pre-specify what you're going to test. Then you have a test that has the proper size. Because you have one hypothesis that this is the policy that's going to be the most effective. But in general, so here we could have said, well, the effect is going to be larger in poorer areas. But this is something where if you just do that, you throw millions of data because you have lots of other dimensions you would like to use, and who knows, you cannot think about all of them ex ante. So this pre-specification seems to be an efficient way to proceed. So machine learning methods are an attractive way to solve this problem because this is a prediction problem in a way. This is now a prediction problem of a causal effect. So that seems to be yes, this is what we should do. So what you could use is machine learning methods to look for the conditional average treatment effect. That's the average treatment effect conditional on a set of covariates that are pre-established at the beginning of the experiment. Now the sad thing, as many of you probably would know, is that it's not that we have results that tell us that in general we have a good machine learning method that delivers consistency, let alone the ability to provide inference for this type of objects. In very specific circumstances, you can develop this causal random foresting that might or might not, that might work. The issue is these very specific circumstances are a set of assumptions that are regularity assumptions that are nice mathematical objects that, to my knowledge, we cannot see in the data. So that's not superb it's an interesting problem, but it's not superb if you, like me, want to give someone policy advice. Because if I can tell them under some assumption that I cannot tell you if they are satisfied, it might be a correct answer, then I'm not so excited. So that's why me and Victor have, so I went like with this kind of problem to Victor. So we have a very good collaboration, Victor and I, of the kind, I'm asking him dumb question and he goes away and he comes back with a solution. I also provide the data for testing the solution question. So our solution to this problem is to say, look, what the government needs, it's not the whole conditional average treatment effect. What they need is some feature of it. First of all, they need, is there any heterogeneity that is real as opposed to a result of overfitting? Second, if there is one, can you tell me the one variable that really makes a difference between the most affected and least affected thing? So I'm back to a very low dimensional problem now. I'm not going to give you the entire conditional average treatment effect mapping, but I can answer any number of interesting questions you might have on it. So I can look for features of the data. So the idea is to use 1/2 of the sample to do the best we can to estimate the conditional average treatment effect, and then to post-process it in the other half for very simple objects. For example, the best linear projector of the conditional average treatment effect, for example, the effect for the 5 groups from the lowest affected person to the most affected person, or for example, the main characteristics we can see to be different in those most affected and least affected. So I'm running out of time, so I won't go into the mechanism of how you do that, but I'm happy to answer questions if there is on that. And I'll give you the result for immunization. And what's really cool is that here, so this is example with random forest, but you can use whatever you like. What is very interesting is that we do find significant heterogeneity that is real because it's in our post-processed sample. It's not overfitted, where you see that some groups have negative effects. The least affected group have negative point estimate. The most affected group has a very positive point estimate. So number one, there is meaningful heterogeneity in this sample. And believe me, we've tried that in any number of samples. It's not always true. Often you think there is heterogeneity, and when you try to look for the best linear projection, it tells you it's 0. All the heterogeneity you thought you have was pure junk. So here we have real heterogeneity. And number two, it's actually, there is one variable that really comes out as driving the heterogeneity, is the baseline immunization rate. So in places that have low immunization, to start with, the effects are larger. So that's very nice. That comes whichever way you measure immunization. It's the only thing that comes systematically comes out. So that means that we can tell the government, you can do this if you want to do this, just target the places which have low immunization to start with. We're very lucky that it happens to be the result because, of course, that's what they want to do because it's also good for equity, but it wouldn't necessarily have to be like that. So in conclusion, I hope I kind of convinced you that that's a big policy issue, and then that's a collaboration with the governments, with us, academics, and a very strong organization in the field, that's JPAL South Asia. Many tools that have to do with data, so the data collection tools, and here I really want to give a shout out to Sana to put that together, the randomized control trial and the whole organization of it, social networks, machine learning. And at the end of it, really leads to actionable policy advice. The government is interested in scaling this up, and then we are going to help them in trying to put that together. Thank you.
Fascinating talk. So I think we have just a bit of time for some questions, 5 minutes, I'm just told, for some questions. So Dora will be walking around.
Hi, my name is Khalil. I'm involved in development work in the Eastern Caribbean and in certain parts of East Africa, and also in your DDP program. So my question is about the social networks. How were you able to control for problems of misinformation along the way? If you start with one person and by the time you get to like the 10th person, the information has completely changed. And also, have you tried to implement this in other sectors? So is there a cross-sector generalizability? So maybe in your education intervention, so maybe insurance or credit? Okay.
So great question. So in this case, we really have, it's a super reduced form. We didn't really try to trace whatever the path of the information. So we have no idea. We just know that we gave them some SMS and we have more immunization at the end of it. So not everything was lost. But we were worried about that, which is why we tried both gossips and trusted people, thinking that in the case of immunization, which is something personal like that, it might make a difference. And we were actually surprised to see that it's really the pure gossips that does the best. The first time we did this experiment was a technology diffusion, so it was about cell phone promotion. So that was a kind of another sector. For us, immunization was already a generalization from that. But I think people are interested in looking at using it for example, agriculture. I haven't seen it used for education yet, but you could think about it. Whether it will generalize to this application, I don't know, but it is worth asking. The kind of the basic underpinning is as the advantage of being very, very, very simple. It's all about how the information diffuse in a very trivial model of kind of spread of information. So that's an advantage in the sense that it's portable across contexts, and that's a limitation in the sense that if anything else is important, like trust or things like that, it might break down.
Yeah. Hi. So my question is about the difference between the gossip and the trusted gossip. So it seems that if you're trusted gossip, the effect of being a gossiper sort of goes away. So, I mean, my question is basically, do you think that actually people, if they ask for a trusted gossip, name different kind of people? Because normally there should be a subset of the other. So basically then you could say, okay, if you're an untrusted gossiper, you're even more affected than...
Yeah. So I think that the trade-off is between maybe the trusted gossip is more trusted, but it's more difficult to identify them. Because we don't have a model that says that people know who is actually trusted. So I think you basically lose in gossipness by focusing on what the subset of the gossip that people think are trusted. They don't do a very good job at saying that someone is trusted. And therefore, they have people who are not particularly trusted because they're not really good at doing that, and who are less gossipy than the best gossip. Imagine it's like, if I ask you, you cannot get the best gossip, so you get some random selection until you get the right number, then you would have less people who are less good on average than just the pure gossip.
Okay, thanks.
Hi. Yes, you. Hey, thanks for the talk. Learned a lot. It was really great. I had just a thought on the feature that you pulled out as potentially predictive is, of course, whether or not there's low immunization rates. And sorry, can you hear me okay? Yeah. So, of course, that would make sense if you intervene when there's low immunization rate. I guess the question would be, what is the second most important feature? And I have one to propose. And I'll give a little bit of context. So I'm familiar with two municipalities in India, which are very different. One is in Trichinopoli, where you'll have central figures who are important, but the rest of the individuals don't really matter. And another is in Altara, which is in Kerala. And that municipality has a very diffuse topology in their network, where you could basically pick one person at random, tell them something, and within a day, everybody in the village knows. I was wondering if you had done any research on the topologies themselves, and I know you mentioned those are hard to measure or to actually get, but that might be an interesting feature, and it might be another problem of could you try to infer what the topology is of a municipality or a village based strictly on some features. So
in this data, we didn't collect network data, but piece of free advertising, we have collected social network maps for 70 villages in Karnataka at repeated points, actually, where we've interviewed everybody about their relationship with everybody. And that data is available on, you can find it from my webpage, and people have used it to look at not only the shape of the network at a given point in time, but how it evolves over time. So these very questions can be answered. And it's in those cases where we actually had the full network maps that we did the first experiment on gossips. And we tried to look a little bit whether the impact of the gossip depends on the shape of the network and where the gossip was located, et cetera. And nothing like jumped as being super pertinent. But that doesn't mean it's not there. We were a little bit of starting to get the impression that we were data mining, so we stopped.
Thank you for your talk. And there was there was one slide with a color diagram illustrating efficiency of different kinds of combinations of influences, and within many of them led to negative effect. How do you explain it? Because anyway, all of the combinations are like additional information.
Yeah.
Yeah. So how could it be that so many of them lead to negative effect?
So I think most of these negative numbers are actually zeros because they were already with no correction for the fact that there are many things we are testing at the same time. Most of the p-values are fairly high. So I think there are a lot of zeros. So that's the first order questions. The one that seems to be negative and significant, if you really believe the p-value the way they are, is the gossip only. And that one, I think it could be from this backfiring of someone repeating the mantra of immunization is important, without any concrete information going with it. But I might be over-interpreting. So before even interpreting that number, I would look for correcting those numbers for multiple inference somehow.
Okay, great. So thank you very much again for a wonderful talk.
Thank you.